And let's welcome Michael Doboli, who is going to talk about periodic behavior of the minimal Colijn-Plazzotta rank for trees with a fixed number of leaves. Thank you, Michael.
All right, so today we will be using the tools developed by this community to solve an open problem in mathematical biology. Specifically, we will be focusing on binary rooted trees. So what the context here is unlabeled trees where the order of the subtrees doesn't matter. So they're non-plane trees. And in general, these types of trees have been studied a lot. They have been enumerated. They've been put into generating functions. The asymptotics have been studied. The enumeration is called the Wedderburn-Etherington numbers. And if you're curious what these trees look like, they're like this. The biological context here is if you have some speciation events, but you don't actually care what the species are, and you just want to study the shape of the evolutionary tree, this is where the unlabeled, rooted binary trees would come in terms of a biological context. And another thing that has been studied with these trees is a bijection between them and the positive integers, specifically the Colijn-Plazzotta bijection. And the way this bijection works is if we just let T be the set of all unlabeled rooted binary trees, we do a recursive definition. So the tree with just one leaf has rank 1. And if it has more than one leaf, as most trees do, we let the left subtree be L of T, or the right subtree be R of T. And specifically, since the order doesn't matter, you can just arrange them so that the left one is the one with higher rank. And then you do this formula to it. And this kind of seems contrived, but as I'll explain later, it's basically just motivated to make this entire thing a bijection. And in practice, we have, let's just work through an example here quickly. The way you would calculate the CP rank of this tree is you would just use a recursive definition and work down to the bottom. So you would start at the root. You would say, okay, what's the CP rank of the left subtree? You go to the left subtree. What's the CP rank of this left subtree? You keep going until you end up with the tree with one leaf, which has CP rank 1. And then you go to the right subtree, also CP rank 1. And then you use this magic formula to combine the two. And you get that this one has CP rank 2. You go back to this one, 1. And you keep combining it in this way. And the formula works out so that the final CP rank of the entire tree is just 13. And if you're wondering where this formula appears from, it is basically contrived so that if you take the CP ranks in descending order and you make the tuple of the CP rank of the left subtree and the CP rank of the right subtree, and remember that we're doing this so that this rank is going to be greater than this rank. If you do this in descending order, this will be in lexicographical order. So the next one would be 3, 3, 4, 1, and so on. So that's where that previous formula comes from. And it's all just designed to make this property hold. And this property is essentially what Colijn-Plazzotta used to show that this thing is in fact a bijection. And I've been using the word CP rank freely, but I am just defining it as the integer that the tree gets mapped to. And if you'll notice the CP rank, the way we define it, it doesn't really have anything to do with the leaves. We just defined it in terms of left and right subtree. So you can ask the question, if we fix the number of leaves, or in a biological context, if we fix the number of species, like what type of CP ranks, what range of values can this take? And the person who studied this was Rosenberg in 2021. And specifically, he found a recursion for the maximal and minimal CP rank on n leaves. And if A sub n denotes the minimal CP rank and B sub n denotes the maximal CP rank, then you get these two recursive formulas for A sub n and B sub n. And if you are curious what the values look like, the A sub n is strictly increasing, but it grows kind of slowly and kind of weirdly. It looks like it, jumps around and like at occasional spots. It's a bit of a strange thing. And B sub n is a little bit nicer in that it just goes straight up. And so the natural question is, okay, what's the asymptotic growth of these? Because these are just numbers. And Rosenberg finds the asymptotic formula for B sub n that grows super exponentially with a constant beta. And he finds an upper bound on the minimal rank, and he shows that it's bounded by an exponential growth. And the natural question is, well, why can't we get an asymptotic formula for this A sub n? And this question was actually posed at last year's AOA. And Xianghui Huang, along with others in the room, identified that A sub n is actually a divide and conquer recurrence, and we can use the tools developed for that, for this problem. So let's get into how to do that. So this is how A sub n is defined again. And if you'll notice, it bears a lot of similarities with the divide and conquer occurrences that we've seen over the last few days. Specifically, the one that we're going to try and massage this into is the divide and conquer with just the ceiling. And the reason why we're going to ignore this floor is basically we'll just be rearranging this and then take logarithms at some point, and we'll put this into the toll function. So that's why we're just going to be looking at the ceiling. But if you're curious about how we actually go about doing this, we write A sub n first, we unpack the binomial, we complete the square. This is just, we're getting this into a nicer form. Okay, this is a little bit nicer. And now you take the logarithm, you do it, and then you finally get that A sub n can be rearranged, that the original recurrence can be arranged into this newer recurrence that is much more clearly a divide and conquer occurrence. But on that note, it is worth noting that this is a very unusual divide and conquer recurrence, because the toll function here is defined in terms of something that relates to the lambda. Also, the toll function is sometimes negative. So this is kind of a odd looking thing. And if you're worried that this might cause issues, fortunately, the theorems that we'll apply later just basically require a uniform convergence result and not any of these other issues that this would seem to pose. So it still does go through because uniform convergence holds, but it's a bit of a oddity to look at. And specifically, the result that we will be applying is Huang et al. 2017, which suppose that we have the divide and conquer recurrence that we have, if we have this uniform convergence criterion where this certain sum of, in terms of lowercase g, converges to this infinite series uniformly, then we can say actually precisely what f of n is in terms of a one periodic function and something that is smaller than it. In particular, you can say that it is this one period function p, where p is defined in terms of something that is kind of like the fractional part, but just a little bit different, and q. And in our particular case, applying this result here, we get that because mu sub n is bounded by a constant for all n, which you can show, but we don't show it here, you then use the Weierstrass M test to deduce that the desired uniform convergence hold. And because of that, we can just use the machine we had before to say that lambda n is precisely of this form. And now, if you remember, lambda n was defined in terms of g of n, which is then defined in terms of a of n. So if we just unpack all of that, we already get the asymptotic expansion of a sub n in terms of a periodic function. So already we're in better shape than we were at the beginning of this talk, because we already have that it's something, it grows with something exponential. But this isn't a very satisfying answer in the sense that it's defined in terms of this mysterious p. So you might want to get more numerical results out of this. And the way you do that is you have to study p. And in particular, you have to study the extrema of 2 to the p of t on t from 0 to 1. And studying this will allow you to then say what type of constants this, because right now we have an exponent that varies on n. So if we study the extrema, we can say precisely between what types of values this exponent can vary between. And to get a better sense of here, we will plot 2 to the pt. In particular, we plot an approximation. And so if we just approximate this sum to 10 terms, which actually isn't all that bad because mu grows very quickly to 0. But if we just plot this, we get a plot that looks like this. So this thing is very, very funny looking, but its minimum seems to be here. Well, it's one periodic, so here. And it seems that the supremum, or it's not even clear based on just this approximation, but it appears that whatever is the highest thing is somewhere up here. And it's just, if we were going, like, take this approximate, it's unclear if there's like a value here where it attains the maximum, or if it's like attained as you approach 0 to the right. So this plot is more just to get a better sense of what's happening here, more than an actual proof. So with this in mind, we will actually do a proof. So we will first show that the exponential order is lower bounded when we consider t equals 0. So just to turn that into a concrete math problem, we say, okay, we want to show that the minimum is at t equals 0. That's equivalent to showing that the minimum of p of t is at t equals 0. And now plug that into the formula we had before. And this is the inequality we're trying to show. And we rearrange this. So we are trying to show that this quantity is positive. And just based on how this looks, there's not really a clear plan of attack. So this is what we will use for our plan of attack. I'm fairly certain that nothing stupider works because I tried the stupid things first and they didn't work. So I think you have to do something at least like this. So you first separate into the small k and then the large k. For the small k, we handle it computationally because you turn it into something that's just basically something with finite cases, and then you check them. And then for large k, you handle basically the only thing we know about mu is that it grows to 0 very quickly. So you show a precise bound for how quickly, for when it starts to get very small, and then we use that upper bound to handle the large k. This is just very abstractly what we're going to do. More precisely, we prove two lemmas. So the first lemma is for k greater than or equal to 11, the large k, and we show that this holds. So if you replace it's this inequality relating general k with something fixed, well, fixed with a t on the right. And lemma 2, which is the small k, is just, it's hard to see from this angle, but there's a sum for k equals 1 to 10 on the left-hand side and another sum, k equals 1 to 10 on the right-hand side, and they relate different quantities together. And if you're wondering how these quantities actually connect to each other, if you just assume these lemmas 1 and 2, you immediately have the inequality you're trying to prove, because you just take the original thing, we're trying to show this is positive, you take out the first term, you split the sum into k equals 1 to 10 and 11 to infinity, and then use those lemmas to this thing turns into this times 2 to the negative k, this thing turns into this times 2 to the negative k, and the entire thing just goes to 0. So if those two lemmas are true, the actual thing you're trying to show is immediate. So now the problem is, okay, how do we show those lemmas? And lemma 1, if you recall, is the big K lemma. We're trying to show for any k greater than or equal to 11, this thing holds. So the first thing we do is, well, we only have one variable here, the t. So let's move it to one side. Okay. The left-hand side is interesting because if this is not, like, other than at the discontinuities, it's actually fairly nice. It decreases, but the only issue is that sometimes this will become an integer and then it kind of isn't nice anymore. So there's all these discontinuities. But because it decreases with t, this means that instead of checking all t the 0, 1, you actually just have to check at the discontinuities because that's the only place where this inequality could possibly break. So now instead of showing this for all t in 0, 1, we instead just have to show it for when it's a discontinuity, which is when this thing is an integer, or when t approaches 1 from the left. And if t approaches 1 from the left, that's trivial because this thing just becomes this and cancels and just 2 to the negative t greater than 2 to the negative 1, okay? And if 2 to the k plus t is an integer, well, this means that we can write t very precisely of this form for some integer n. So now if we just plug in this form for t, we get a new inequality. So basically the strategy here is we're just simplifying the original thing down until we get something that is much more reasonable to work with. And in fact, instead of showing this inequality, we can show something even stronger, which is you just replace 2 to the k plus n on the bottom with this. And now, or equivalently, you get this. And finally, we can say the thing we were saying before about mu going to 0 very quickly. We have this another lemma, which shows that mu sub for a sufficiently large x, mu sub x grows like mu sub x times this is less than some constant. And if we just assume this lemma for granted, you can prove it, and we do in the paper. If you use this lemma, you immediately get this thing. The details are important or not particularly important, but you just basically do a simple like triangle inequality argument and then this lemma replaces this with this, and then you get the constant you want on the right side. So this is abbreviating some details, but this is more or less how you show lemma 1, the large K case. And now the small K case is this sum, which looks kind of ugly, but at the very least, we know K is between 1 to 10. So we kind of, like before we start similar, you move the variables to one side. And then like before, this left side decreases unless T is at a discontinuity. So it suffices to consider the two cases. Like before, it's trivial for as you approach 1 from the left. And now, because you only have finitely this many discontinuities, because K is from 1 to 10, this is now just a purely computational task. So you put it into a computer and verify it. So now this is lemma 2. And like we said before, if lemma 1 and lemma 2 are correct, then the original thing is correct. So we have our lower bound. So, all right, cool. Now we know how low the exponent can get. Now, how high can it get? And going back to the picture, this was the one that seemed a little bit more confusing because it seems to be as you approach T from the right, this is where it gets maximized. So let's try proving that. So in particular, the plot suggests that the supremum is attained as you force T to 0 from the right. And of course, like before, we put that into math terms, and we have, this is the inequality we're trying to show. And we do the same exact methodology as before. We split this into a small k case and a big K case. And the lemmas, which are particularly important, are basically the same exact thing as before. You split it, the smaller case and the bigger case. And you use the exact same methodology as before, where you reduce this to an inequality that just depends on the size of mu. And then this one you can check computationally. And now, assuming they're true, the entire thing works out. And we won't prove lemma 4 or 5 because it's pretty similar to proof of lemma 1 and 2. So now we can say the supremum is the limit as you take T to 0 from the right. So now we know the lower bound and we know the upper bound. And the natural question is, what's the average? And Huang et al. 2017 has a method that allows us to do this. Well, first off, you have to clarify that the thing is actually defined, and you can do that by showing that P of T is bounded and continuous almost everywhere. So the integral is a well-defined thing to work with. And it's just, you have this sum here, and when you take the integral, it's just begging to be swapped. And then of course you have to verify that you can do that, but you can. And then if you do the swap and then run the computations, you get that this is the integral of P of T, this infinite series involving mu of n. And if you recall, P of T we don't really care about. We care about 2 to the P of T. So we'll just use Jensen's inequality to get a lower bound on 2 to the P of T. And so we can say that the mean value is at least 1.286. But an important caveat here is that that we're actually studying is 2 to the P of log 2 of n, and this is not equidistributed. So this thing is actually it's only an approximation. It's more of it's purely an approximation. So we will conclude. So we first found that the formula that has the asymptotic expansion depending on this one periodic function. And we studied this one periodic function more to deduce that it has its minimum at T equals 0 and its supremum as T approaches 0 from the right. And that is, we can deduce that the lim inf of Ta of n over 2c1 and equals 1, and we found in lim sup of this, where c of 1 is defined as 2 to the p of 0, like the minimum of 2p, well, just the minimum of 2p of t, and c of 2 is the supremum as we approach it from the right. And if you want numerical constants, you get that the base of the exponent is somewhere between 1.246 and 1.334. And so if you want to actually convert this to just an upper bound on a sub n, because q of n in our case will be positive, as you can show, this actually just gives us a straight upper bound on a sub n, which improves upon Rosenberg's 3/2 to the n, because C2 is less than 1.5. And in a sense, this, not even in a sense, this is the best possible exponential upper bound that you can get for all n greater than 1, because we showed that the lim sup of an over C2 to the n is 1. So you can't replace this C2 with anything better. And moreover, as a sanity check, Rosenberg 2021 actually showed that a sub 2 to the n has this asymptotic expansion, where his alpha coincides with RC1. So this work also verifies what had been previously known about the asymptotic expansion of a sub n, except we also find it for general n instead of just powers of 2. And it confirms the intuition that the maximal rank, which is super exponential, will grow much quicker than the minimal. And moreover, people in this field have wondered about this problem, specifically in this book about tree balance indices. If you're wondering why, what this talk has to do with tree balance index, it's basically that this biological context where the CP rank comes up in is that it can be used as a proxy for tree balance. So people in the field have wondered about this problem. And yeah, so we would like to also acknowledge Daniel Kren and Stefan Wagner for their conversations at last year's AOA to help identify the link between this and the divide and conquer occurrence, and also some members of the Rosenberg lab who helped us with this work. And these are our references. And thank you.
Yes.
If is the CP rank known for a uniformly random tree with n leaves?
I don't think so. I think
There's
the
no
only
result
things
about
that are known are just, yeah, the only for deterministic. I don't think that's been studied before.
Are there more questions? Oh, Svante wants me to do some exercise. Thank you, Svante. I had 3 pain au chocolat at the break, so.
Okay. So if I understood here, in this case, this periodic function P is not continuous, but it has, so does it have an infinite number of discontinuities which are dense?
Yeah, it has countably many discontinuities. Yeah.
Yes. Okay.
But yeah, it's not continuous. I believe it's continuous in the case where you have the floor function in there too, but because it's only the ceiling function and no floor, it's not continuous.
Yes, I mean, here, since you had your upper and lower bound both were attained at 0, just as one as the right limit and otherwise 0, so.
Yeah.
Yes.
Yeah. This.
Yes, but then if your picture there suggests that you have lots of other smaller jumps as well, yes. Okay.
Yeah.
Yes, because as you know, I'm mainly used to most cases we end up with continuous P of T, but here you get a discontinuous one, which must be because of your toll function, I guess.
Yeah. And it's because I guess it's not continuous that we have to do the whole analysis about the rest of this, because if it was
Yes.
yeah.
Yes, no, very interesting. Thank you.
More questions? Okay, if not, let's thanks Michael for the very nice talk. Thank you.